section 4.5 is about Euler paths, circuits, and Hamiltonian paths and circuits. It's a little bit shorter because it's not a 100% deep dive. There's so much more that we know about Euler paths and circuits, and this is really just an introduction. So let's retitle that, an introduction. So if we start at a vertex and trace along the edges to get to other vertices, we are going to create a walk through that graph. A walk in a graph is a sequence of vertices such that every vertex in the sequence is adjacent to the vertices before and after it in the sequence. Okay? If you go on a walk that touches every edge exactly once, then the walk is called an Euler path. So if I have my graph, we'll go with P sub 3, so it's got 3 edges and 4 vertices, and I go on a walk, this is an Euler path. It goes to every edge exactly once. An Euler circuit could be something like K3, where if I start at 1, I end at the where I started. Of course, if a graph is not connected, there's no hope of us finding such a path or circuit, right? So if my graph was just open dots, right? There's no way to find a path or circuit. So it doesn't work for forests unless they're connected, which would make them trees. So a graph has an Euler circuit if and only if the degree of every vertex is even. And a graph has an Euler path if and only if there are at most 2 vertices with odd degrees. So let's take a look at K6. K6 is the connected graph, right? And because it's connected, we have a theorem. I'm going to sketch this real hastily, but we have a theorem that says that if I have K sub n, every vertice is degree n minus 1. So in K6, every vertice is 6 minus 1, which is 5. Okay, so it's not going to have an Euler circuit because every vertex is odd, not even. And it's not going to have an Euler path because there are actually 6 vertices of degree 5. So for this, it's going to have no path or circuit. For K7, we know the degree of the vertices is 6. So this is going to have an Euler circuit because every vertex is even. For C7, that's just this guy right here. It's a connected loop. I could tell you right away, if you just look at it, you can see, oh yeah, I could start here and go all the way around. But it's also important to note that every degree is 2, so because every degree is even, this has an Euler circuit. And P9, that's the path with 9 edges, 2, 3, 4, 5, 6, 7, 8, 9. This isn't going to have an Euler circuit, but you can see it would have an Euler path, right? I can start at 1 and hit every edge along the way. So this has an Euler path. Let's look at 2 more examples. So here I have K5 and K7. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Let's just pretend I drew this all out, right? Remember that it has to be completely connected, and every vertices has to go to every vertices. So these ones right here, these have, each of these go to 7, so they all have degree 6. Okay, each of these down here, they all have degree 7, because each of them goes to the 7 in the group 7. So because all my degrees are odd, there's no path or circuit. Then when it comes to K27, I've got 2 that go to 1, 2, 3, 4, 5, 6, 7. So each of these have degree 7, and each of these have degree 2. So because there are at most 2 vertices with odd degree, we have an Euler path for this example. The last thing I want to talk about is Hamilton path. So a Hamilton path is a path which reaches every vertex once. So Euler paths and circuits were all about them edges. Now we're about our vertex and vertices. So Hamilton cycles are the same except they start and stop at the same vertex. And there's no simple step for test for whether a graph has a Hamilton path. So for which Kn does K sub n contain a Hamilton path cycle? Well, this is kind of easy, right? There's K1, K2, K3, K4. You can see that all of these would have a Hamilton path cycle. I just count out hitting all the vertices, not all the edges. So that's an introduction to Hamilton paths.